Good afternoon, students. Myself, Dr. Divya Gildayal, in continuation with my lecture series for AKTU B.Tech first year engineering physics syllabus. Now I will be completing fiber optics in this second lecture of mine. In the first lecture, I told you about optical fiber working on the principle of total internal reflection of light. The formula for numerical aperture is under root n1 square minus n2 square, where n1 and n2 are refractive index of core and cladding respectively. I told you about acceptance angle equal to a sine theta maximum under root n1 square minus n2 square, numerical aperture acceptance angle. Now, we are going to discuss about number of modes and cutoff parameter of optical fiber. See, basically there are three types of optical fibers. In a very broad way, if I classify them, they are single mode, multi-mode graded index fiber, and multi-mode step index fiber. These three are demarcated on the basis of refractive index. They are characterized by the way the light is traveling down the fiber, and they depend upon the wavelength of light that is being used and their internal geometric structure. So the number of modes that are being supported by an optical fiber is obtained by V parameter or V number. This is usually mentioned on the optical fiber. And it is like cutoff parameters such as normalized frequency of cutoff, etc., which we refer to as the V number or the V parameter. Mathematically, suppose lambda naught is the wavelength of monochromatic light beam which is propagating in a multi-mode glass fiber with core diameter D, N1, N2 being the refractive indices of core and cladding. Then V number mathematically is given by pi, that is 3.14, into D, which is diameter of the core, lambda naught wavelength of monochromatic light beam that is being used, and N1, N2 the refractive indices of core and cladding. We know from the definition of numerical aperture that numerical aperture is given by under root n1 square minus n2 square. So the formula for V number becomes equal to pi d upon lambda naught into numerical aperture. The total number of modes that one fiber can support is equal to V square upon 2. These numerical values are required when we design an optical fiber. So the V number, V parameter is larger than unity. Every mode has a particular value of V parameter, and remember that below this value, the mode is going to get cut off. And of all the modes, only those modes will be propagated for which cutoff frequencies are less than the V number. So V number can be reduced either by reducing the numerical aperture, because you see V number is depending directly on numerical aperture. If I decrease numerical aperture, V number will be decreased directly, or by reducing the diameter of the fiber. See, V number is also dependent upon the diameter of fiber. If I change the diameter, V number will change. If I change numerical aperture, V number will change. So discuss the structure of an optical fiber. What are the various types of optical fiber? Explain their advantages and disadvantages. Very favorite question of your AKTU exam. You have to learn this. It can be a 10-mark question also in your exam. So there are two types of optical fibers depending upon the refractive index of core and cladding, because this refractive index is responsible for all the formulas I have told you: numerical aperture, acceptance angle, V number, all are depending upon the refractive index. So the step index optical fiber or the graded index optical fiber. Step name has just been given from the usual English literature word step. That is the steps we go one by one, and graded according to the refractive index. So step index optical fiber, in this, core has a refractive index which is staying constant, and cladding has a uniform refractive index, and obviously refractive index of core should be greater than that of cladding. So this is basically the outlook of a step index optical fiber. You can see it is in the form of a step, and the refractive index of this fiber will go as abrupt change at the core cladding boundary. They obtain their name from the step shape, and rays entering at different angles travel different paths and emerge out of the fiber at different times along different directions. Graded index optical fiber, the core has non-uniform refractive index which increases from the axis towards the cladding. See, remember the changes of refractive index. Whole game is of refractive index, and the cladding has a uniform refractive index. The entire ray is continuously bent and travels a periodic path along the axis. The rays entering at different angles follow different path with same period both in space and time. So this is basically, you can see grading 1, 2, 3. It depends. So here we have given you a diagram which is comparing the step index and the graded index. See here the step form, and here the helical shape. If it is a 10-mark question, you have to draw this diagram and give this table in detail. Path of light in step index fiber is zigzag. Path of light in graded index fiber is helical, that is in the shape of a helix. Core has a constant refractive index. Refractive index of core here decreases continuously. The attenuation is like decrease in the output or sort of disturbance. I will tell you detailed attenuation right now only at the end of this lecture. Here the attenuation is less. Refractive index for a step index fiber is expressed as, see, we know that here n is going to stay constant for a longer time. Here n will be varying as the square into 1 upon r by a to the whole square. Now, a very simple question, numerical, is asked on V number usually. So first write the formula. V number is equal to 2 pi a by lambda into numerical aperture. Now a single mode step index fiber is made with a core of diameter 10 micrometer. Micro becomes 10 to the power of -6, and this is coupled to a laser that produces 1.8 micrometer light. Its core glass has a refractive index of 1.55, and the maximum cutoff number for the given fiber is 2.405. Find the maximum value required for the normalized index difference and find the refractive index for the cladding glass, and also find the fiber acceptance angle. See, first we are going to write down the formula for the cutoff number or the V number. We have been given 2A is equal to 10 micrometer. Lambda is 1.8 micrometer and V has been given to you. So numerical aperture becomes equal to V into lambda upon 2 pi A. We keep the value of V here. We keep the value of lambda. We don't need to convert this micrometer into meter because here these units will get cancelled directly, and you get the answer for numerical aperture. Normalized index difference, del is equal to half into numerical aperture upon n1 square. You just keep the mathematical value directly here. And the cladding index required by the formula for fractional refractive index, and maximum acceptance angle is sine inverse of numerical aperture. So the optical fiber cable is also called an optical waveguide. The energy in the cable is propagated by electric and magnetic field vectors of the famous EMT wave, which can be analyzed by Maxwell's field equations. Now, these Maxwell's equations have a discrete set of solutions, which are called modes. So this word, the number of modes propagating in an optical fiber are determined by a parameter called horizontal wave number, which is given by 2 pi a divided by lambda into numerical aperture, where a is radius of core, lambda is the single wavelength which you are using, and Na is numerical aperture. Optical fibers are basically or broadly divided as single mode, multi-mode, and graded index. So more theory on this for your 10-mark question. Fibers, see, single means one. So fibers having narrow core, allowing only one wavelength to pass through them will be the single mode fibers. And numerical aperture and acceptance angle for this will obviously be small, which will allow the transmission of only one fundamental mode. They are used in very high speed where you want less dispersion, large bandwidth, and long distance transmission. Multi-mode fibers having relatively a wide core, and they are allowing different modes to pass through them are called multi. Multi in English means many. So they are allowing there are two rays traveling along the core, one near the axis called axial rays, whereas the other called the marginal rays. The marginal rays will travel longer compared to the axial rays. And the graded index fibers do not have a constant refractive index in the core, but their refractive index decreases with radial distance from a maximum value of N1 at the axis to the constant value N2, and NR will be given by N1 into 1 minus 2 del R divided by A to the power of alpha whole square root. Now, explain single mode and multi-mode, differentiate the characteristic properties of single and multi-mode. Now, from the very language only, it is clear single is one, multi is many. So single mode index fiber, only single mode is propagated. Multi, large number of modes can be propagated. Single mode, difference in the refractive indices of the core and cladding is very small. Difference in the refractive indices of core and cladding is large. Here in single mode, numerical aperture or opening is small. Here, numerical aperture is large. Modal dispersion, obviously, when it is in the single ray of it is transmitting, the dispersion will be less. Here, dispersion will be more. But single mode are more expensive compared to the multi-mode index fiber. One numerical on V mode, I have already discussed it, as you just need to keep the numerical values in the formula and you get the answer for V mode. Optical fiber, how is it basically transmitting? See, block diagram, simple input via optical fiber output. So how am I putting the input inside optical fiber? Via a modulator. See, laser or LED is used as a source of light capable of generating an optical signal of desired frequency for my specific experiment, and signal for modulating the output light beam from the laser according to my experimental requirement. I will modulate this input frequency, then it via carrier source and transmitter. This goes inside my optical fiber setup. Here at receiving end, here, once it is out, we have a photo detector. This is the component capable of converting this light which is falling on it into my required or desired electric signal. An electric amplifier is then used which processes the signal and output is obtained. So in short, input will be modulated by my modulator, carrier will transmit it to my optical fiber. Outside the optical fiber, photo detector will change this signal into electrical signal that I will amplify and accordingly use it for my experiment. Now, what happens in optical fiber is that attenuation, that is this word itself, it came right now in my lecture above. I told you I will tell you about attenuation. Attenuation means the loss of light energy as the light pulse travels from one end of the optical fiber to the other. So the light pulse of specific amplitude is applied to one end of the optical fiber, but the output light pulse at the other end of optical fiber will be much lower in amplitude compared to the input. Main reason for this is the loss in signal. Maybe it is optical phenomena. Loss in signal can be due to absorption, scattering, dispersion of the light signal. So if I am putting an input of 98%, my output is going to be less, say 90%. Rest of this 8% has got lost either as getting absorbed, scattered or dispersed. This is a signal loss of an optical fiber, and optical fiber is designed especially useful for low transmission losses as compared to metallic conductors. The signal attenuation within an optical fiber is expressed in logarithmic unit of decibels. So if I put a power of input of pi and output I get p naught, so number of decibels is equal to 10 log base 10 pi by p naught. Logarithmic unit has the advantage that operations of multiplication and division will be converted into addition or subtraction. So if alpha in decibels is signal attenuation per unit length and L of optical fiber, then alpha decibel is equal to 10 upon L, length of optical fiber, log base 10 pi, input power upon p naught output power. Very simple numerical I will show you on this expression. The mean optical power launched into a 5 kilometer length of optical fiber is 120 microwatt and the mean optical power at the receiver end is 4. See, I launched 120 and output I am getting only 4. So the loss has happened because of dispersion, scattering, absorption. Calculate the loss in decibels. So what formula have you done? Decibels is equal to 10 log base 10 pi by p naught. Pi 120 microwatt, p naught 4 microwatt. Don't convert because you are dividing. It will get cancelled. Simply put this numerical value. You get 4 3s are 12. So log base 10 30. Find out the log value of log base 10 30. Multiply it by 10, you get the answer. Signal attenuation per kilometer of fiber will be given by decibels divided by length of my fiber. So what are the dispersion losses in optical fiber? The distortion or broadening of optical fiber signal propagating along the fiber is called dispersion. Smaller is the pulse dispersion. Greater is the information being carried by the optical fiber. That means losses should be less. If losses are more, optical fiber is not of good quality. Main reasons for losses are because of waveguide structure. The light rays in the fiber follow different path and take different times during traveling. This dispersion is called waveguide dispersion. Material dispersion, the refractive index of fiber core depends on the wavelength of light. So different frequency components of input signal travel with different velocities, and hence the pulse gets broadened. Intermodal dispersions can be the spread of group velocities, can be the dispersion in the intermode dispersion. So total, we can sum up that total dispersion can be given by the sum of waveguide dispersion material, intermode dispersion material, or the pulse broadening. So explain dispersion and attenuation in optical fiber, and a simple numerical on Pi, P output upon P input. What are the advantages of optical fiber? See, optical fibers are very easy to maintain, lightweight compared to the original copper cables, easy to use, they are economical monetary wise, they deliver signals at a very less cost, they have a larger lifespan compared to the traditional copper cables, and they have a noise-free transmission communication. So quickly, let us revise what did we do in optical fiber second lecture today. We learned that the types of optical fibers which come are single mode, multi-mode, and graded. Single mode, refractive index remains constant. Multi-mode, it allows different wave modes to pass through such fibers. And in the graded, they are not having constant refractive index, but a decreasing refractive index. Single mode are comparatively better as they have less scattering, less dispersion, but yes, they are less comparatively more costly. We learnt about cutoff number given by pi d upon lambda naught under root n1 square minus n2 square, and optical fiber, how it transmits. It has an input via laser light. It is modulated by modulator. The carrier wave carries it to the optical fiber. Inside the optical fiber, it suffers the phenomena of total internal reflection received by a photodetector. Amplifier amplifies the signal, and according to our experimental use, we process the signal and receive it at the output. Input-output variation is known as attenuation, or the loss of signal. When I gave some amount of signal, output comes out less. This has happened because of scattering losses, absorption, dispersion, and otherwise optical fiber compared to electrical cable is lightweight, easy, economical to use. Thank you. Ada.